Welcome back to Miss Lisa's YouTube channel, where we talk about all things math and science. Not really all things, just the things I want to talk about. This is physical science, and what we are going to be talking about today is in your book, Chapter 6, Temperature and Heat. This is a class primarily designed for homeschoolers, but if you like the way I explain things, come on in, like, share, subscribe. I have a goal. I'm trying to get 1,000 subscribers so I don't have to videotape and then upload it on YouTube because it takes forever. I want to just stream it live. So I'm up to like 270 now, so I've got a long way to go, but share it with your homeschool groups, with your friends, and tell them free science. All you gotta do is go buy your book. I use older edition public school books, so they're cheap, and you can usually find them on eBay, Amazon, or Alibris. So anyway, the book we're doing right now is, oops, sorry, it's not an earthquake, it's me moving this book. It's Glencoe Physical Science, but I actually am having you do two books. This one and an old Addison Wesley Physical Science book from the 80s. The reason why we're doing the physical science book from the 80s is they've got great labs for homeschoolers using things that are easy to get. You know, you don't have money to spend tons and tons of money on a science class, so I try to pick things where you're going to be able to do labs with more everyday common materials and still get the same learning for much cheaper, because I was a homeschool mom and I know that, you know, budget is important. We can't spend all the money we want on homeschool. All right, so what we're talking about today is temperature and heat. So first of all, what is temperature? First, we say things are hot or cold, and but we're going to talk. Let's talk about this, as Rhett and Link would say, that it has to do with the kinetic energy of the molecules. Here I've drawn atoms on the board, much bigger than actual size, and all matter is moving. And that moving matter has kinetic energy. So it's how much it's moving. All matter moves. Even your book that's sitting on the table that looks like it's completely still, the atoms are vibrating. And they continue to do so until it cools off to a point that's called absolute zero. It's hundreds of degrees below zero. And that is the point where theoretically matter would cease moving. And we've not reached it. We've gotten close, but we've not reached it. So we don't know that for sure, but that's according to the theories, to what we believe. So temperature is a measure of the average kinetic energy of something. So when you take something's temperature, what you're doing is you're finding out how much these molecules are moving. Things that are hot, their molecules move faster. Things that are cold, their molecules move slower. Now, this is the part where I've argued with students in the past. I used to teach public school. I'm teaching public school again, but for a while I was the homeschool mom in the middle. But when I taught public school last time, I taught physical science, and I had the student, and I told him this that I'm about to tell you, that in science, cold doesn't exist. Cold is only a lack of heat, and heat comes from kinetic energy. Okay, that was the truth I laid on him. And he was a real country boy. We're in Georgia, and he'd say, "No, Miss Blackburn, it ain't so. Cold exists because I can feel it." And I'd be like, "No, it doesn't. It is a lack of heat. What you're feeling is you're feeling less heat." And he'd say, "No, Miss Blackburn, that just ain't so. Cold exists. I can feel it." Okay, so I had him in 9th grade. 10th grade biology, I asked him, "Have I convinced you yet? Does cold exist?" "No, Miss Blackburn, I'm sorry, ma'am, but no." Then 11th grade, I taught him chemistry. "Okay, Kenny, do you believe that cold doesn't exist yet?" "No, Miss Blackburn, I can still feel it. Sorry, ma'am." And then senior year physics, I taught him. "How about now?" "No, Miss Blackburn, I'm sorry, ma'am." So I always think Kenny, my student who I could not convince. I had 4 years to do it. I was the only teacher he had in public school, high school. I was the only science teacher he ever had. He got me every year. We got along fine. He enjoyed my classes, but he just did not believe everything I said, that's for sure. He was a skeptic. That's good. It's good to be a skeptic. So anyway, cold doesn't exist. It's a lack of heat. They used to think it existed back a long time ago. They thought it was an invisible blue fluid. Don't know how it's invisible in blue, but that's what I read. And it would flow into things. So you would catch cold. This invisible fluid would fly around and it'd get in you. And then you could do things like have some brandy and it'd make the cold leave you. So on these old shows, they would have the dog with the brandy around his neck going out through the Alps trying to warm people up. So that's what they used to believe. But now we know that cold is a lack of heat. And that heat is it has to do with the vibration of the molecules in the atoms. All right? So heat, temperature, energy. These have slightly different definitions. You got to kind of keep them straight, but they're all related. So the first one is temperature. And it is the measure of average kinetic energy. And remember, kinetic energy is energy of motion. Potential energy is energy of position. Okay. The next one is thermal energy. You'll find out in your book on page 159 if you're following along. And the thermal energy is different in that it is the sum of all the kinetic and potential energy. So you can sort of think of this as the energy of motion, but it's also the energy that is stored in the chemical bonds in the molecules. And that those bonds can be broken and more energy released, the thermal energy. So I always ask students, which one has more thermal energy? A teacup full of boiling hot tea or the ocean that is cool to the touch? Which one has more thermal energy? And kids always say it wrong. I would ask you if you were here with me, and they'll say the boiling hot teacup. Nope. That would have a greater temperature, yes. It would have a greater average kinetic energy, yes. But the ocean is full of potential. All those chemical bonds ready to break. So all that potential energy is much, much more. So the total thermal energy of the ocean is way more than the little teacup with not much in it of boiling water. Now, the way your book talks about it is they say that you've got two beakers and one has twice as much water in it than the other, and they're the same temperature. Do they have the same thermal energy? No. The one that's twice as much water would have twice as much thermal energy, more molecules with bonds that we can break, more potential energy. Their kinetic energy might be the same, but their potential energy is more. Okay. The other thing is, and that's why mass has an effect. If something has more mass, it's got more thermal energy. Now, what is heat? Here's our next one. Heat is energy that flows from an area of high heat to an area of low heat. Now, I'm going to use the word cool or cold, which we know doesn't exist, but you can think of it that heat always flows from hot to cold. So, say you're cold and you go hug somebody who's warm, their heat is going to flow out of them into you. And I try to do that because I'm always cold. Even in the summer, my fingers will turn blue and I'm cold. I'll be running in August in Georgia at the track and my fingers will turn blue because I'm cold. I know, it's just terrible. So I'm all about trying to get heat to flow into me. But heat flows from more heat to less heat, or from hot to cold. In our common speech. So, and the reason why is because there's all this energy, things moving around, and the molecules are bumping into other molecules, which cause them to start moving, and that heat flows from the area of more heat to less as bumping occurs. So this is the heat moving. And we have a lot of things that work on this principle. We do both heating and cooling. It's very big industries in our society. And we're going to talk more about that as we go on into this chapter. All right. So heat flows. And so what they have is they made some homemade ice cream. And they put the cool milk and cream and sugar and vanilla flavoring in the ice cream maker. And then they surrounded it with rock salt, ice cream salt, which lowers the temperature, and ice, which makes it colder than 32 degrees Fahrenheit or 0 degrees Celsius. And so then the ice cream mixture is much warmer than the surrounding ice. The heat will flow out of the ice cream mixture into the ice, lowering the heat of the ice cream mixture until it freezes. And so when I teach this in public school or when I've taught with homeschoolers, a lot of times we will make ice cream at this point because, you know, you got to do the fun labs too. And we'll do it by putting a big gallon Ziploc bag full of salt and ice, and then a little Ziploc bag, we put our ice cream mixture in there. And when you do it, you zip it up and you give it to the kids and they shake it until it makes ice cream, and then we eat it. So that's a fun little lab that y'all can do too. If you want the exact amounts to put in, Google it. It's out there everywhere. Science teachers have done this for decades. So it's the ice cream lab where the kids make homemade ice cream by just shaking the Ziploc bags. And we used to do it even when I taught public school. We would do it sometimes using soda, like strawberry soda, and sweetened condensed milk. And we would make it that way too, because that way it's shelf stable. It tastes, but then the other teachers are like, why are you making that nasty ice cream? You should make good stuff. I have my kids bring in milk. So they all switched to using real milk, real sugar, real vanilla. And so I did too. But I started off doing the cheap stuff. That was a little easier. And I had kids who liked it too. Our little fake strawberry soda ice cream we used to make. Anyway, you can look them both up online. I'm sure the exact recipes are out there. Okay, so now the next thing is called specific heat. I know you're like, so many words. You can get them, I promise. So what is specific heat? It is a physical property of the material. Some things hold heat longer than others. For example, if I heated up a pot in my kitchen and heated up the pot and then turned it off, I'd go back in not very much time at all and it will have cooled off again because it's made out of metal. But if I had that pot full of water and I heated it up to boiling and then turned it off, I could come back a long time later and that water would still be warm. Water has a higher specific heat than metal. Things with a high specific heat take a long time to heat up and a long time to cool off. Things with a low specific heat will heat up quickly and cool off quickly. And for those of you who load and unload the dishwasher, you know this. You open up the dishwasher. It is extremely hot. You reach in there to get something out of the dishwasher and you don't reach for the glass. That glass is still going to be hot. You reach for the wooden spoon. It's going to be fine. You put that away. Get anything wooden, take that out first. It's cooling off fast, low specific heat. Next, you can take out the metal. The metal's going to cool off next. You grab that metal out, put away the forks, put away the spoons, and you won't get burned. Last, you take out the ceramics and the glass because they're going to hold that heat longer. They're going to stay hot longer. So a lot of things you have noticed without really thinking about it over the years because you've been living in this world and you've been observing physics whether you realize it or not. Now lately when I have asked kids about the dishwasher so that they realize things have different specific heat, I have come across all these kids who never unload the dishwasher. I'm like, isn't your mama making you do chores? Don't you have some chores to do? And they're like, no, I've never noticed that. And I'm like, well, I think you should unload the dishwasher right after it runs and touch everything and notice what cools off first and what holds their heat. And that can be another little lab you can do this week too. You can make ice cream and you can unload the dishwasher. So there you go. Touch everything. You need to do it right after it finishes running while everything's still kind of hot. If there's water on it, it'll keep the heat longer because water has a very high specific heat, which is really important. We would have no life on this planet if it doesn't. And we're going to talk about water and its high specific heat, I think, on this page. If you look at the bottom of page 161, you see water molecules. Water is shaped like Mickey Mouse. So the head is negative and the ears are positive. The head is oxygen. So I always draw it as unimpressed Mickey Mouse. I'll draw it right here for you. So here's Mickey Mouse. He's unimpressed because he's got positive ears and a negative mouth. And it's because oxygen is a bully and keeps the electrons, if you remember, are negative more, and the hydrogens end up without them and they end up positive. It is called a polar molecule. It has a negative end and a positive end. And so what do opposites do? Attract or repel. That's right, they attract. So that makes water a sticky molecule where the water sticks to itself because of these forces of attraction. Your book calls it strong bonds. They're not actual chemical bonds. There's something called hydrogen bonds, and they're forces of attraction between the positive and negative because opposites attract. Next idea. This stickiness makes it where it's hard to get the energy into the water and get it moving and vibrating more because it's stuck so tight it doesn't want to move. So it's very hard for it to heat up. Once it heats up, it holds the heat and it doesn't give it up. And this is why it gives us life on our planet. It's because we are covered with water. Other planets, we're the water planet. Other planets don't have all of our water. So in the day, they get extremely hot where it couldn't support life. And then at night, it gets extremely cold where it wouldn't support life. We're covered with water. All during the day, the extra energy from the sun goes into the oceans and it just absorbs it and heats up, and it takes that energy and it's all stuck together, and it takes it a long time. Heat. Then the earth turns away from the sun at night, and all that heat that was given to it during the day then releases at night, keeping it warm at night. So the oceans, we could not have life on our planet without the oceans being made of water with its high specific heat. It makes our planet have constant temperatures that can support life. Perfectly designed, right? Isn't that cool? All right, so that is, water is a coolant because it has a high specific heat. It can absorb a lot of heat. And actually, water can also be a heater because it has a high specific heat. It's because it gains and loses heat slowly. So we know this on our skin. When you sweat, water evaporates and it cools you off. So evaporation takes the energy in the water out to the atmosphere and cools you off. So evaporation is water evaporating, becoming water vapor, is a cooling process. The opposite is condensation. You walk into a sauna, you walk into your bathroom where someone just took a shower and there's all this water in the air, then the water moving around in the air will hit your skin, and it's a little cooler, and it'll slow down, and it'll give its energy to you, and it'll heat you up. So condensation is a warming process. Evaporation is a cooling process. They're opposites, and they take away energy if it's evaporation. They give energy if it's if it's condensation, and it's a warming process. So it's really got water. Water's perfect. It's absolutely perfect to be our sweat, and it's also perfect for our oceans. No life without it. All right, so there is a math problem on page 162, which is the heat equation. The heat equation is this. It's either Q for heat. Don't know why. Sometimes you'll see a capital H for heat. That makes more sense. But usually in chemistry, it's a Q. In physics, sometimes you see it as an H. And it is, the heat is equal to the mass times the specific heat, which is a constant. It's a number that is a constant, is a property of the material, times, this is a triangle, it's the Greek letter delta, and it means change or difference. So it's times the change in T temperature. But it looks like cat. So I like the formula written this way. Your book writes it a different way, and it doesn't spell cat. But it's easy to remember because cats are nice, warm little creatures. So we can remember that the heat equation is the heat equals cat. Mass times specific heat times the change in temperature. Where you get the specific heat is it's in tables. You look it up for the substance. It's a constant based on what the substance is. Now, the the definition of specific heat is in your book. It is on page 161, and they say that it is the amount of heat needed to raise 1 kilogram of material by 1 degree Celsius. When I teach it, I usually teach it as the amount to raise 1 gram by 1 degree Celsius. So sometimes in different charts, the specific heats are different depending on the units. So like the amount, and you can measure that heat in joules, that's a unit of heat or energy, or you can measure it in calories, that's also a unit of heat or energy. So depending on the chart you have, sometimes you see the specific heats different. Like some specific heat charts have the specific heat of water as 1. Your book has it as 4,184, and it's because of the units. The specific heat of water is always the same, but it can have different units, just like in Celsius, water boils at 100. In Fahrenheit, it boils at 212. I'm thinking about the next thing. Water boils where it boils. The temperature is the same. It's just the units make it a different number, either 212 or 100, depending on if it's Fahrenheit or Celsius. Same with specific heat. All right, so we can measure specific heat in a device called a calorimeter. It's a real insulated thing, and you put water in it. You throw in there what's been heated up, and then you see, and you put a thermometer in it, and you see how much heat goes from the thing that's heated up into the water. There's also called a bomb calorimeter, where you burn stuff and see how much energy is given off. So there's different ones. You can make your own with an insulated cup, with a styrofoam cup. But I don't usually bother with that in physical science. In chemistry, we do some labs with that. It's a little more specific, and we do some labs with calorimeters. So I wouldn't worry about it too much. You're going to be doing different labs this week. I will put it, the homework's always in the description. So I don't think you're going to be doing anything with a calorimeter, but it's just it's an insulated cup you use to do heat experiments in. All right, so how is energy transferred? I already showed you that it can be transferred through collision, and that is through conduction. If something is once heated up and it's moving and it bounces into the next one and makes it move and bounces into the next one, that's conduction. And there are things by their nature that are good conductors and ones that are bad. The ones that are bad conductors are called insulators. A good conductor is a metal spoon. You take a metal spoon, you stick it in a candle, and in a minute you're going to let go, because that heat is going to transfer from the candle down the metal spoon to your hand and burn you. However, you could take a stick out at your campfire, you stick it in the fire, and you can hold that stick. You can even roast a marshmallow on the end, catch the marshmallow on fire. Your hand's going to be okay, because wood is a good insulator, not a good conductor. It's why, like, you're stirring your food with a wooden spoon, you're not going to get burnt as much. You have to be a little more careful if you're stirring that food and cooking with a metal spoon. You might, if it's all metal, that you might end up having the bumping molecules use conduction to transfer the heat to your hand. All right, there's another way that you can transfer heat, and it is called convection. Convection uses fans. So they make something called a convection oven, and it's what they use in England. So if you ever watch the Great British Bake Show, their ovens are convection ovens. So they'll put their cake in, and then they turn on the fan, and it blows the air around. It makes the heat move around faster, and it actually cooks stuff faster. Those ovens really have not caught on in America the way they have in England. I remember when they first came out, they were like, everybody's gonna start using these because they cook so much faster, and people didn't buy them. People like knowing that their pound cake takes this long to cook, and they're okay with it taking that long. They want their recipes to turn out the same way Grandma made them, and Grandma didn't use a convection oven, so they don't either. But whenever you have a fan helping the temperature change quicker, that's convection. So convection uses a fluid that moves to carry the heat. Now, the weird thing is, in physics, a fluid can be gas or liquid. So it could be a gas blowing, like in the convection oven, or it could be currents of water, where you heat up water and then you blow it, or some other liquid where it moves. But gases and liquids are both considered fluids. I know it doesn't make sense, but it is, because they both do the same thing, that the heat can move with the fluid, and it can move faster. It can be carried along by the fluid. Okay, so currents can transfer heat. It's very important in our world. We have currents like the Gulf Stream that carries heat along. If it wasn't for the Gulf Stream, England would be a very, very cold country. But the water goes down from Africa over to the Caribbean, where we are in Georgia, we're near that. And then it goes up, back up to England, and ships come right on it and go fast, but it also carries heat, and it helps our earth have good temperatures for people to live all over it as these convection currents happen. And it talks about in your book also about the convection currents around. Another way heat can be transferred is radiation. The sun shines. There is empty space, the cold void of space between us and the sun. But that sunlight gets here and it starts causing molecules to move and heating everything up. It heats up our atmosphere. It transfers very nicely through gas, transfers pretty good through liquid water, and then it hits solids, and it doesn't transfer as readily. It's, radiation is stopped by a solid, but radiation can heat things up. We use radiation like with a toaster. The coils get all bright and hot, and then radiant heat can go across from that. But the sun is our best example of radiant heat and how it reacts. Now, controlling heat flow is very important. If you're cold, what do? You go put on a coat. Things that are insulators are fluffy and they have air pockets in it, because that keeps convection from happening. Also, gases don't transfer heat as well as solids. So as long as there's air pockets, you have insulation in your attic or maybe in your garage roof, and it's puffy. It's got puffy little air pockets that keep the air from moving, and it makes things stay warm. Even like up in the Arctic, you can build a house out of snow or ice, get inside, build a fire, and you're warm because of the insulating properties that's in the ice or snow. When water freezes, it expands. It's why ice floats, and it's got this little hexagon shape of these air pockets that are in it. Ice has air pockets in it because of the way the water molecules align. Because of that Mickey Mouse shape, they align where the opposites attract is good for them. Doing that makes them have these little air pockets that makes the ice float in liquid water. Liquid water is closer. And those air pockets are insulators. So ice can actually be used as an insulator where it stops heat transfer. So also it talks about that you can control heat flow, and how in nature so many animals are perfectly equipped for heat flow. That penguins are black on the back to absorb heat, that they can have warm fur coats like sheep, and that desert animals have reflective scales that help reflect the radiant energy away from them, helping keep them cool. We use insulators. I talked about that. We insulate buildings. We wear insulated clothing. And then the last thing it talks about in this section is thermoses. How does a thermos work? There's a picture of one on page 170. When these were originally developed, they were called Pope Dewar Flask. But then thermos was the brand that started making them. And just like saran wrap, we call it the brand name now. Or Band-Aids, that's another one. where we call things, instead of calling it an adhesive strip, we call it a Band-Aid, the brand name. So how a thermos works is it's vacuumed on the inside. There was air on the inside of it. It's got an outer layer and an inner layer, and they pump all the air out, so there's no air molecules on the inside, no air molecules to transfer the heat. They also originally were made out of glass, and they were mirrored so that any heat that was there was reflected, and it could not be transferred. Nowadays, they don't just make them out of glass and mirror, because you would drop your thermos, it would bust, and it'd be no good. Now now our insulated bottles a lot of times are stainless steel, and they've got that reflective property, but they're not going to break like the old glass ones used to. So there's not very many old thermoses like from the 60s, because they used to be made out of glass and they would break. But they worked really good. It's amazing how long, and the ones they have now, like the Yeti and stuff, they can heat a long time. All right. Now, the last section is about using heating systems. There's different kinds. There's a forced air system where something is heated up, and then they blow, and it blows the heat into your house. If you have a furnace that, it can be like that, it blows, and it blows the heat throughout your house. Another one is a radiator system. We had this in my college. I called it Rad the Radiator. And it has a place where the water's heated up, and then the hot water is sent through the radiator system. And the radiator had a big surface area, and it would let that heat into the room. You see it on Buddy the Elf. He gets all scared about the radiator. He had never seen one of those, so he calls his dad at work being scared about the radiator because it's making a scary noise, because the radiators give off steam. If it's too hot, that steam has to release somewhere, and they make a lot of noise. They bang and all that, and you'll forget it's there, and you touch it, and you get burned on it. Also, there would be a pipe taking the hot water up to the next floor, and you'd forget and touch that and get burnt too. So that's the only time I've ever lived with the radiator, was when I went to Erskine College in Due West, South Carolina, and I was in Carnegie Hall. We said Carnegie, not Carnegie. So then there can also be electric heating systems. They have these a lot up north, where the heating coils are placed in the floor or the floorboards. I don't know of anybody down here in the South that has one. It just doesn't get that cold here in the wintertime. We actually, at my family, we don't turn on our heat in the winter. I told biology class. I was telling them about that. I have a son who had asthma, and the heat would really bother him where he couldn't breathe. So we just heat our house with fires in the fireplace, and we put on sweaters and stuff like that. And we usually do not turn on our heat all winter. It just doesn't get that cold here. Our house is very insulated, and we usually don't need it. We'll use like an electric blanket at night, and that's all. We don't. And then we have fires in the fireplace, and we don't turn on our heat. And it's because of the way it dries the air out so much. We have a heat pump, and that's what we're getting there, about ways to heat. And what heat pumps do is they act to change heat to where it is it can make it cool in the summer or hot in the winter, and it seems to just be much more drying than regular furnaces. So the electric heating system. All right. Then it talks about solar heating. Some people have solar panels. You can have a passive solar system where it's just big windows where the sun comes in to heat up, or it could be an active one with solar panels where the sun energy is captured, and that's how it is used for heating. What I've heard now is that they have roofs that are actually solar panels, and they can you can heat and cool your house and actually run your house. All of it's electricity with these solar panel roofs. It's so cool. We just got a new roof, and we, of course, that wasn't on the table with our insurance paying for it, but I thought it would be really cool to have. I wonder if a tree branch fell on it, though, if it would break. I don't know enough about them. It's probably the future, though. It's probably what everybody's going to have, are solar panel roofs. So thermodynamics. There is a relationship between thermal energy, heat, and work. And the study of those is a branch of physics called thermodynamics. That heat and work increase thermal energy. And that kind of makes sense. You sort of noticed this already. Your car is a machine. It's working. You go to Dollar General and go buy something. You come home, you touch the hood, it's warm. Because this car has been working, remember the physics definition of work is a force applied where something is moved a distance. That because of friction and other things like with your car, you have combustion going on, that you end up with heat as part of work. So there are two laws of physics that go with this. And remember, laws beat theories. It's like rock, paper, scissors, and laws beat theories, and there's two of them. They used to be stated a little different than they are now. And I think the old way of stating it is more clear and it's easier to understand. The reason why I believe they've changed the way it's stated is because of evolution. And I will explain what I mean by that. And remember, rock, paper, scissors, laws beat theories. So that's, I'll explain what I'm talking about. Okay, so first let me tell you what the two laws are. The first one is the first law of thermodynamics, and it is part of the law of conservation. The law of conservation says matter and energy are neither created or destroyed, but only changed from one form to another. So it is, in particular, looking at the energy part of it, the heat energy part of it, that heat energy cannot be created or destroyed ever since creation. It can only be changed from one form to another. So that makes sense. You know, you want to burn a fire. Where do you get the log? Well, where do you get that fire? You burn a log that has energy stored in its chemical bonds. Where did that energy come from for it's stored in its chemical bonds? Well, it came from the nutrients that the plant got out of the soil and from ultimately sun energy that came from the sun. And where did the sun get its energy from? It got it from fusion, from fusing hydrogen into helium, and because of E equals mc squared, part of that mass is converted into energy. Where did the elements come from? The hydrogen and the helium. Creation. It came from the beginning. So back to the beginning, whatever that beginning is, scientists agree that matter, atoms, and energy are neither created or destroyed. They're only changed from one form to the other. Now, there had to have been a beginning. It had to have all started somewhere, but they really don't address that. They only address that at this point, you can't create it or destroy it. You can only make it change from one form to another. Law number one. Law number two. It's the second law of thermodynamics. It's also called the law of entropy. And it says that things do not move from disorder to order unless acted upon by an outside force. So like your room, it's a mess. It is not going to clean itself unless acted upon by an outside force. You can go in and make it more orderly. Another way to look at it more on a chemical level is, imagine there's an old tractor out in a field. If it is left there long enough, it's not going to get prettier and newer and nicer. No, it's going to rust. It's going to fall apart. It's going to decompose. It's going to go from order to disorder. And I've seen that. We live near the Atlanta area and we love Six Flags. And there's a ride there called the Dahlonega. And when I was a kid, as part of the Imagineering of the Dahlonega, because it was based on the gold rush that was in Georgia, in the town of Dahlonega, that was before the gold rush in California. We actually had two little things of gold discovered in Georgia before the California one. But the Dahlonega one was second, according to the town of Villa Rica. Theirs was first. So, but a lot of people say Dahlonega is first. It's a little controversial. But if you go to the Gold Museum in Villa Rica, they'll convince you that they had gold first, that it was found there first. So anyway, we had a gold rush there. And so, but it was before Minor 49er, the 1840s. So this was in the covered wagon days. So at Six Flags, they had this covered wagon that was sitting there to be part of the Imagineering of the Dahlonega ride. Well, I've been going to Six Flags since I was a little bitty baby. And now I'm not. As you can see, it's been decades. And over the years, Six Flags has just left that thing sitting there. And it used to look like a covered wagon. And then, of course, the cover got gone first, and it had the little curved metal going around. And then those were gone. And then the wheels rotted off, the wooden wheels. And then it was just a cart rusting with no wheels. And then it started falling apart where it's rusting and rusting. And still, last time I went to Six Flags, which was just a couple of months ago, yeah, we had to wear a mask, and it was very hot and much a pain, but we went anyway because we had season passes. We rode Dahlonega, and now it's just like 4 pieces of metal laying out in the field. So because no one did an outside force on it, just left to itself, things move from order to disorder. You see it like, imagine I have a beaker here and it's full of water, and I put a drop of food coloring in it. Given time, it will spread out. It will become less organized. It will go to more disorder as it spreads. Now, why is it controversial? Let's go back to what I said in the beginning. According to the theory of evolution, which I think is very important for you to know because it's a very important theory influencing scientific thought at this point in the year 2020. According to the theory of evolution, things went from disorder, primordial muck, to order. It has gone from disorder to order. You have extreme order. If you want to know about how extreme your order is, watch my biology videos. You have amazing circulatory system. You have an amazing excretion system. Your pee is amazing. The fact that your blood is purified by your kidneys and that waste is gotten out of you through your pee is amazing order. Unbelievable order. So for things to have gone from disorder to order, this law is a problem. Now, the answer to that evolutionists say is time. Given enough time, it could happen. Like given enough time, there's any possibility is there argument to that, but it really does. There is disagreement among science because of this. And this is one of the things I want you to take as a takeaway from this class is often students get the idea that science is done. There's nothing else to discover. If scientist says there is no more argument. It's done. And that is so far from the truth. There is so much more to be discovered. If you believe in evolution and you think that it is the truth, there needs to be more discovery about this because we have a problem with this second law of thermodynamics. So there is more that needs to be discovered. If you disagree with it, there's more that might need to be discovered about that too. Science is not done, and scientists do not all agree. They argue, and these are scientists with science degrees. They argue about things like physics and biology and things that have happened in the past. Science is not settled, and there is still lots to be discovered. So I just don't want you to get that wrong impression that scientists are all-knowing. And I know there are scientists who would like you to believe that, but it's not true. Scientists are not all-knowing, and there's still lots we don't understand. And there are parts of science that contradict each other. So there's more out there to learn, and that's cool, right? It's good to learn. All right, so now let's talk about our next part, converting heat to work. What they do is they go through and they talk about the internal combustion engine, how it works. If you look on page 177, you see what's going on in your engine. You have these chambers, and in them are pistons. And a piston you can think of like a shot. And so they've got these little chambers, and the shot part goes down, so there's a little place, and in that place it gets a squirt of gasoline and a spark and air, and it makes a little explosion. And when it does, it pushes this down, and then others are going off that then push it back. And so this pushing down happens over and over again. And as these things are pushing down, then that is changed, where then you look back on page 176, that it turns this rod going through your car, and then that in turn causes the tires to turn. So it goes throughout the car, and it transfers the energy from one to another. And when it does that, there's heat is involved. First, there's heat in the little explosion of the gas exploding with the spark from the spark plug, and that's heat. Explosions cause heat, the ones with gasoline. And then as all of these components of the car are moving, there's friction, and friction causes heat. It turns out that only 25% of your gasoline makes your car go. All the rest is lost as heat to the environment. And so one way of making cars more efficient would be if there would be a way to reduce friction, to use more insulators to keep the heat making the car go forward, instead making the gasoline make the car go forward, instead of losing all that energy to the environment. And then the next thing it talks about, and we've already talked about sweat, but it talks about refrigerators. How does a refrigerator work? Well, refrigerators have a coolant in them, a chemical that can absorb heat, and it will become a gas and a liquid, and as it changes between gas and liquid, it causes the heat to move. So how the refrigerator works is the heat that's in the refrigerator, it goes into the chemical of the coolant, and then this coolant is pumped around, and then because of changing it from liquid to gas, the heat is removed and released into the kitchen. So you probably have noticed underneath your refrigerator, if you feel there's hot air coming out. That's the air that was pumped out of your refrigerator. And we used to, when we would wash our shoes, we would put them at the bottom of the refrigerator to dry, because it'd dry out real slow instead of beating it around in the dryer. So later I had a rack where you could dry shoes in the dryer, but my new dryer doesn't have that rack. But it's fun when it does. If not, you gotta go put them in front of the refrigerator. And I always remembered as a little kid thinking, why does the refrigerator make heat? It's supposed to be making things cool. It's taking that heat out of the refrigerator and it's coming out underneath it, putting it in the kitchen. All right, so that is it. Look in the comments and I'll tell you what labs you're going to do with this. And like, share, subscribe. I'm Miss Lisa. Science is great.